Time to start. Welcome everybody. Today, our secret seminar speaker, Professor Yasuaki Hikida from Yukawa Institute Theoretical Physics and Kyoto University. We will talk about very interesting subject. So here title is Complex Shadows of Three-Dimensional Discrete Gravity via Holography. So please start.
Thank you very much. Thank you for the introduction. And yeah, as I talked a little bit, so I was actually a postdoc at Korea about 20 years ago. And yeah, I actually visited Sogan University and gave a talk at that time. And I remember at that time, I also talked about somehow related to string theory on cosmology or something like that. But yeah, I don't remember quite, yeah, concrete. But today I want to talk about dS3 correspondence. My title of talk is Complex Shadows of Three-Dimensional Digital Gravity via Holography. And this talk is based on collaboration with Henyu Chen at National Taiwan University and Hayato Kanno at YITP and Yusuke Taki, YITP, and Takahiro Ueto, Kushiro College, National Institute of Technology. And the reference is this. And this work actually continuation of the work with Tatsuma Nishioka and Tadashi Takayane and Yusuke Tashi and published in this paper, and also Henyu Chen and C Chen and published in this paper. Okay, yeah, let's get started. So it is sometimes useful to complexify geometry when we consider quantum gravity. And a canonical example is given by no boundary proposal by Hartle and Hawking, and geometry is something like this. So this geometry can be written like this. This is a kind of complexified metric of sphere. So this is a metric for d-dimensional sphere, and there's one other dimension, and the other dimension is complexified. And if this extra dimension is real, then this is just a sphere. And if it is just a pure imaginary, then this is digital. And so now we want to consider some kind of connecting these two geometry, something like this. And let us say more concrete about it. So we assume that the universe starts from nothing at say u equals 0, and approaches our universe, maybe namely a digital space at u to infinity. So universe starts from nothing means this term vanishes at u equals 0. So u equals 0, we assign this is 0, and this means theta takes this value. And the important point here is this n can take integer value, any integer value. So therefore, we have a lot of geometry, candidate of geometry, which is labeled by one integer. And so question here is which geometry is allowed when, for example, when we consider quantum gravity, we have to sum over all possible geometry, and which geometry we should sum over. So this is the question. And this kind of question was addressed by these authors. And this paper, Kontevich and Siegel proposed some criteria to criteria for allowable geometry. And this is this one is actually easy to understand. This is just a field strength for Q-14. So this is just a kinetic term for Q-form field. So this means a path integral of free field for Q-1 form must converge. But if we apply this criteria to this geometry, then only n equal -1 and 0 are allowed. This is exactly what Hartle and Hawking consider. So in this way, we can reproduce the result of Hartle and Hawking by this method. But of course, there's a lot of question about this this criteria. What is this?
I'm sorry for
Yeah.
disturbing
Yeah.
you. I have very simple questions. So
Yes.
you take the metric in the complexified of the ST plus 1 very special time. So
Yeah.
it's it maybe include the Euclidean de Sitter space. Do you is it right?
Yeah, right.
Do you have any reason why you started this kind of the very specific form of the Euclideanized metric?
No reason.
No
Just
reason.
this is an example. So this kind of criteria can be applied to any kind of geometry, and this is just one example. This is just a little bit generalized Hartle-Hawking's geometry. So this is just one example, one simple example. And what this is one canonical example.
According to the original paper by the Hawking, and it's in your case there is something conformal factor L square. So maybe you will consider L square later. So this one is something different from the metric taken by the original paper. So my question is just a simple.
Probably right.
Yeah. Do you have any reason like taking like
no
this kind of
no special reason, just
okay.
a simplified problem, and you can start from more complicated metric, and apply this. And
sorry, Kikita-san.
Yes.
Why this Q-form field is necessary to have some reasonable geometry?
Yeah, that's a question. So why Q-form field? So this is discussed in Witten's paper, but actually I think there's no clear reason why Q-form. So this is
I see.
a proposal by sorry. This is proposed maybe. This is proposed by Kontevich and Seeger, and Kontevich and Seeger are mathematicians, so maybe they consider some simplified, some simple criteria, which is somehow inspired by physics, but not related via physics. For example, if we take Q equals 0, this includes Q equals 0, and for Q equals 0, there's no so -1 form field. So Q equals 0 is not related to some physics. And so just in that,
Anyway, this statement implies without Q-form field, we cannot have Hartle-Hawking analytic continuation. Am I right?
Sorry. So
I mean,
if we assume this kind of metric, then there's some series of geometry allowed labeled by n, and among them only this one is satisfy this criteria
with this Q-form field.
Yeah, right.
So my question is, without Q-form field, there is no way to have this kind of complex geometry.
So
without Q-field.
Yeah, I think that's the question. So in order to determine allowable geometry, then we need some criteria, and I think we not just think that only, for example, scalar field. If kinetic term scalar field is well defined, then maybe it is okay. But they require this kind of criteria for all Q-form fields.
I see.
And this is, I feel, too much. But maybe this is because mathematically, it makes mathematically well-defined problem. And
Okay.
for example, this does not include tensor field. So graviton is a tensor field with two spin 2, and this is not included. So I don't think it is this condition is concrete. Concrete criteria. But this is a starting point. This is what I understand. And for example, so Witten, so I think we can use consider two canonical example. One canonical example is this one, so Hartle Hawking, and the other is car black hole, complex version, weak rotated version of car black hole. And actually, this does not satisfy this criteria. So, so weak rotated version of car black hole is rejected by this criteria. And this is, this means I think this criteria is too strong.
I see.
But yeah, but in that, they also he also says that we can consider also car black hole in ADS, and in that case, this criteria is satisfied. So maybe there's a good physical. So even in a Witten's paper, he discussed about this criteria, and this is quite good, but this cannot be the complete one. So this is also written in Witten's paper. So
okay,
yeah,
thank you.
Yeah. So actually, this is one of motivation why we started to this project. So we want to propose another way, a different way to determine allowable complex geometry. And here we use dS3 correspondence we have proposed recently. So, dS3 correspondence is not well understood. And so maybe this kind of work is also reveal property of dS3 correspondence. This is actually my main motivation. But anyway, dS3 has not been well understood if we compare to well-studied ADS-CFT correspondence. I think there's many reasons of this, but one reason is there's not much concrete example available. And one famous example is proposed by Aninos, Hartmann, and Stromicher, and this is duality between higher spin gravity on 4-dimensional digital space and 3D SP and vector model. And this is kind of analytic continuation of Klebanov-Polyakov proposal, which is a duality between higher spin gravity on 4-dimensional anti-digital space and 3D OM vector. And now we are we have proposed 1-dimensional lower version of it. So we propose duality between 3-dimensional digital gravity, higher spin gravity, and some CFT, 2-dimensional conformal field theory. And this is not the way we construct this one, but today I want to explain this duality as a analytic continuation of so-called Gabadego-Bachmann proposal, which is a duality between higher spin gravity on dS3 and some 2-dimensional conformal field theory. So this is a introduction. And next, I want to introduce our proposal of dS-CFT correspondence. And then I will talk about complex saddles of 3D Chern-Simons gravity. Then I will determine the allowable geometry from dual to the CFT. then I will study more about the structure of this Lewis theory and dual CFT, and then I conclude this talk. Okay. Okay, let me start from dS3 correspondence. I think you know lot about ADS-CFT correspondence. For ADS-CFT correspondence, we compute partition function of gravity theory, and the partition function of gravity can be computed from dual CFT. This is a proposal of GKP Witten relation. And so now I want to consider dS3 version of it. But in this case, fundamental object in Dojita space is not partition function, but given by wave functional of universe. And the wave functional of universe is constructed by integrating out over integrating over field living on the bulk, and we assign some boundary condition as future infinity. And the proposal here, actually there's many versions of dS3 correspondence, but I'm talking about all the version proposed by Maldacen and Strominger and Witten. So this is actually Maldacen's version of proposal. And the proposal here is this wave function can be computed by dual CFT as a generating function, correlation function. This is quite similar to GKP Witten relation, as I said, but it's different. And one difference is this is a wave functional. So this wave function itself is not physical observable. So in order to obtain some physical quantity, then for example, if we want to have a partial function, then we have to take square root of it and integrate over all boundary fields. So relation between CFT and bulk theory is quite complicated because of this kind of relation. But anyway, once we have some dual CFT, then we can compute some quantity in the bulk. This is the Maldacen version of dS3 correspondence. And for example, if we want to have a partial function, then we compute a square root of this geometry. And actually, this part is real, take real value. And if it is take real value, then this is just a phase. So if we take square root of it, then this part disappears, and only Euclidean part remains. So this is the basics of dS3 correspondence, and I want to introduce our duality as an analytic continuation of Gabalier-Gopakma duality. And there's actually two versions of Gabalier-Gopakma duality, but I will use one unfamiliar version of it. So this is a duality between higher spin ADS3 gravity described by SL and Chern-Simons theory, and some coset theory of this form. And the point here is, so usually we use Basileus theory, but the Basileus as a higher spin gravity, but the Basileus theory has infinitely many higher spin fields. So there's no truncation on spin. And for dimension higher than 4, it is not possible to truncate a higher spin field, but spin of a higher spin field. But in the 3 dimension, it is possible to truncate spin, and this is the version we consider here. And this spin n is related to this n appearing here. And if k is integer, positive integer, then this is so-called double-n minimal model. But now, actually, we want to we will take some strange value of k, and this is main feature of this duality. So, but here we for simplicity we take n equal to. This means we have only graviton. So graviton on ADS is related to now we set this equal to this one. So this is if k is in positive integer, then this is just a Virasoro minimal model. But now we want to take some analytic continuation on this level. So this is a kind of strange theory. But in our previous paper, we have shown that the correlation function of this one with generic k can be computed by Liouville theory. So if we start from minimal model and take non-integer k, then it looks like problematic. But actually, you can show that everything can be computed in the Liouville theory. So in that sense, there's no problem about analytic continuation. So let me go a little bit more. So we have we are claiming that the Einstein gravity on dS3 is related to coset model, and the coset model has some level corresponds to level or central charge, and the gravity theory also have some parameters like ADS length or Newton constants, and I want to relate between these parameters. And for that purpose, I want to use a central charge. So it is well known that in the near the boundary of ADS3, there's a Virasoro symmetry, and the central charge is computed by this one. This is famous result by Brown and Eno. And if we take Newton constant to 0, classical gravity limit, then this goes to infinity. Therefore, large central charge limits correspond to classical gravity limit. And for 2D, this coset theory, central charge can be computed like this. And as I said, so if k is a real integer, then this is minimal model. And in that case, this must be less than 1. So we cannot realize a large central charge if we require unitarity of the theory. So we relax this condition of unitarity. And then we can realize a large central charge if we take k to -2 or -3. Here, this is just a kind of choice. So we take k to -2. Then we just solve k in terms of c, so we can expand in this way. So k is very close to -2, and the difference is somehow related to central charge. And this is a Gabadier-Gopakma duality. And so this is a kind of ADS-CFT correspondence. And I want to consider some analytic continuation to construct dS-CFT correspondence. And the gravity side, actually, this is not so difficult because we need to replace negative cosmological constant to positive cosmological constant, and this can be done by just replace ADS radius by I times digital radius. There's only one dimensionless parameter in higher spin gravity, so what we have to do is just replacing this one. And for instance, now central charge is given by this, and if this ADS radius is replaced by I times digital, then this term becomes something like this. So central charge becomes imaginary in the CFT dual to gravity theory on digital. This is pointed out by Maldacena, and this is well-known fact. So it depends on dimension, but in the 3-dimension dS3 CFT2 central charge of CFT2 is imaginary, and for dS4 CFT3 case, central charge of CFT3 is negative. So it cannot. So dual CFT cannot be realized by unitary CFT. This is a well-known fact, and this makes this is, I think, one of the reasons why dS-CFT correspondence is not well understood. So this dual CFT is not unitary, and there not much is known about non-unitary CFT. But anyway,
I'm
yes.
sorry for disturbing you. I have a very simple question. Yeah, okay, yes. In your matrix, L is something to convert from Euclidean dS3 to ADS3. So one simple question is that Euclidean ADS and Euclidean dS is something different, because Euclidean dS is finite and Euclidean ADS is infinite. So this analytic continuation from ADS to this DS or DS to ADS is there
Euclidean ADS is
infinite space.
mapped to Lorentzian dojita.
I mean, here ADS3 and DS3 all are Euclidean.
No, ADS
no.
is Euclidean, but dojita is Lorentzian. They are related.
So from the ADS Euclidean to DS transformation by analytic continuation is
So it's not.
Is
So it's not.
possible,
It's not difficult to see in a point. So it, I mean, yeah. If you say possible or impossible, it is. It might be impossible, but yeah, we want to do that. This is
okay.
actually Maldacena's proposal, and yeah.
Okay.
So this is Euclidean ADS space in the Poincare.
Okay.
And now we replace LADS by I times L I times LDS. So we have a minus sign here, and now we also shift Z to I times eta. Then this becomes minus eta square, and this minus eta plus dx. Then what's happening? L times
it could be one of assumption in the
L times
in your theory.
yes.
Okay.
And
I will,
yeah.
yeah.
Yeah, this one. So
Yeah,
this is Poincare partial logic.
I understood. Yeah, thank you.
Yeah, but yeah, of course. So we can do this, but in a matrix, but we have put some field on this metric, and the field changes due to this kind of analytic continuation. So there's quite complicated things, and of course now we can do this only Poincare part, and we don't know what happened in other cases. But so yeah, this is, I think, a very important point. But this is Maldacena's trick, and it works quite well. But I think nobody understands why it works. This is quite so this is quite different from the Hartle-Hawking wave function. In that case, we do some analytic continuation at some what is T equals L of dojita space. In a global coordinate of dojita space, we can do some analytic continuation and put some sphere. And this analytic Maldacena's analytic continuation is quite different from that one. but it is believed that both gave the same result. And I think no one understands why both give the same result. Yeah, this is, I think, very important point.
Thank you for your
Yeah,
explanation.
thank you very much for the question. And,
Yeah, I have
yes.
I have another question. So yeah, one page before on ADS. Right here. So the basic question is, I mean, so you are considering some non-integer k.
Yeah.
Yeah. So
Right.
is it well-defined?
So yeah, that's the question.
Yeah.
Yeah, that's a question. So I want so later I will so in the original paper we compute some quantity using some quantity with which is obtained by integer k and analytic continue to non-integer k by hand. But recently we studied this structure by using Liouville theory. So Liouville theory are kind of some extension minimal model. So we can see some structure of how analytic continuation works. This is something. This is actually main topic of this. Yeah. This.
Okay. Okay, I see. Thank
Yeah.
you.
So I mean, I talk this kind of thing later. So I mean, when we wrote this paper and when we gave some talks, then everybody asked this point. So yeah, so that's why we think about this series. Yeah, and yeah, maybe I don't remember how much I talked, but so now this becomes imaginary. So if we solve k in terms of CG, then we have this expression. So things becomes worse. So previously k is negative, but now k becomes a complex value. So things becomes worse, but we want to think about this region seriously in the later part of this talk. So as I said, we found in our in this paper we compute partial function of this side and this side. This side is okay, but this side is quite tricky. We start from integer k and take some this value, and it matches well. But yeah, it is not known whether this kind of analytic continuation is okay or not. So, but yeah, we find the agreement anyway. So let us see what was happening there. So before that, I want to talk about gravity side. So gravity geometry is this one. This one is basically studied by Witten. And this is a solution of three-dimensional gravity with positive cosmological constant. This is called a black hole solution, but this is actually not black hole. There's some conical defect here, and there's some cosmological horizon here, and we are actually living this patch. And associated with this cosmological horizon, this horizon is located where this becomes zero. So therefore, this position, and we can compute entropy associated with this cosmological horizon, and this is computed by this part. And now, actually, now we want to describe this gravity theory in Chern-Simons gravity. There's many reasons why this is many reasons why we want to describe it in Chern-Simons gravity. One is Chern-Simons gravity is useful to consider gauge gravity correspondence, and also if we use Chern-Simons gravity, then at least perturbatively we can quantize the gravity theory. So, but problem is we do not know much about non-perturbative effects. That means we can compute if we fix the geometry, then we can compute something around that geometry, but we do not know which kind of geometry we should take. And this is something we want to address here. But anyway, here we want to we will use Chern-Simons description of gravity theory. So we have two actually Chern-Simons gauge theory, and this gauge field is related to Fairbairn or spin connection in the appearing in the first order formulation of gravity theory. And the metric is computed something like this. So basically this is the same as the Fairbairn. So if we take combine Fairbairn and take trace, then we have a metric. So in this way, we can read off from a configuration gauge field to the metric. And now there's a lot of gauge symmetry, so we can actually choose a lot of there's a lot of freedom, but we can put this form by using some gauge fix, and this A is also fixed to this form, and so now non-trivial part is only here, and this and if we plug this into here, then we can reproduce geometry here, and there's some parameter appearing here, and this parameter is related this curly L this form. And but the problem of Chern-Simons gravity is we don't know what black hole means. So in the metric formulation, there's horizon and singularity, so we can easily see whether there's a black hole or not. But in the Chern-Simons gravity, we have only gauge field, so it is very difficult to see what's happening there. And the proposal, maybe first person proposed this kind of thing is this paper, and they propose that we can construct we can define this holonomy matrix. This holonomy matrix is somehow gauge covariant, and in particular, the eigenvalue of this omega is gauge invariant. Therefore, we can get some gauge invariant quantity from this holonomy matrix. And just like usual black hole is characterized by assuming that after weak rotation of time direction, we assign periodicity such that there's no conical deficit. So here we also assume that holonomy around thermal cycle is trivial.
Sorry, Hikita-san.
Yes.
So in this Chern-Simons gauge theory, basically your connection is SU2.
Right.
SU2
right.
connection. And then underlying manifold, I mean, Euclidean digit 3 is S3.
Right. Right.
So this Wilson loop is defined on S3. Right.
Yeah, that's right. That's right.
But still, this holonomy matrix is non-trivial.
So I mean,
pi1 homotopy is trivial on S3.
Right. So we introduce a conical. Yeah, we have a conical deficit here.
I see.
Yeah. So S3 there's no holonomy. So we introduce a conical deficit, and if we go around that, then we have non-trivial. Yeah.
Okay, now I got it.
Yeah. And yeah, so we construct we use a holonomy matrix to characterize geometry, and we assume that holonomy black hole solution is given by characterized by holonomy matrix, which has a trivial holonomy around the thermal cycle. This is a definition of a black hole by clock. And in the so if we apply large scale transformation around Summer cycle, then we can get same holonomial matrix. And if Chern-Simons theory, the gauge group of Chern-Simons theory is compact and the level is integer, then actually gauge transformation is symmetry of the theory. So even if we act large gauge transformation, then we cannot get different geometry. It's just a same geometry. But now we are working on some complexified version of it. So we are actually considering SL2C gauge group, and the level is non-integer. So large scale transformation actually generate different geometry. And the large scale transformation is labeled by some integer. So therefore, different geometry is labeled by some integer. And we can compute, we can construct such geometry, and we can compute Gibbons-Hawking entropy and associated with symmetry. And this is given by this one. And we want to determine which geometry is allowed from dual Liouville theory. This is what I want to do. So we compute this value from dual CFT, and we want to determine which geometry is allowed. This is what I want to do from now on.
Can I ask a question?
Yes.
So what is the meaning of n in the geometry viewpoint?
This is just the length of Summer cycle. So I didn't write that. So it's not easy.
Can we say that it is related to the deficit angle of the conical defect?
Yes. Just so this is just the deficit angle, but now periodicity is 2 pi n. So maybe this type 2 pi n plus 1 probably. So if we go around many times, then we come back to the original point.
I see. Thank you.
Yeah. So this is same as Witten's geometry actually. So where is it? So this means so we have some we have some theta direction. This is imaginary, and this is real part. And we can start any point, and this corresponds to somehow Euclidean time. So if we change the starting point, then thermal cycle becomes longer and longer. So we are actually doing the same thing as Witten did. Just saying in different words. Is it okay? So as I said, so we can use Liouville description of dual CFT, and the Liouville theory has this kind of action, and now we want to take a strange limit. So central charge is imaginary, and there's some parameter b appearing here, and C and this parameter b is related by this way. And if we solve this one, then we obtain this one. So I mean, so here b appearing here, and this b can be absorbed. Actually, I will absorb this b by defining something like this one. Then b becomes some kind of coupling constant of this Liouville field. So B can be regarded as a coupling constant of Liouville theory. So we do some expansion in terms of B, not C, and but they are almost equivalent. So B inverse is somehow related to central charge. So we are going to take a B to 0 limit where so such that this becomes imaginary time thinking. And then, as I said, a wave function is related to a correlation function. And in this case, wave function is related to 2-point function. This is because black hole can be constructed by putting some particle, and the back reaction of particle create a black hole geometry. So black hole wave function for black hole geometry is related to a 2-point function of Liouville theory. And as I said, we want to take a B to 0 limit and consider some perturbation by B, and considering a leading part of this expansion. And if we so there's a level alpha here, and this if we scale something like this, then eta is related to black hole parameter, something like this. And as I said, if we do this kind of so this B is taken to be very small. So it is useful to take this combination. Then we can think B as a kind of expansion parameter, and the reading on the equation motion can be written like this. And now important point here is let us assume this one is a solution of this equation motion. Then we can shift this amount. So there's no phi here. Actually, this just comes from this one. This is not a part of action, so it is strange to be inserted in the equation motion. But here we regard this whole part as action. So extended, we are considering extended action. So that's why this part appearing in the equation motion. But yeah, this is not so. Yes.
So this equation of motion implies phi c. That is the compact scalar field.
Compact.
I mean, this is shifted to pi in.
Mm-hmm.
What is the meaning of this this one?
Yeah,
I mean, n appears here, right?
Yeah. So problem is what is the meaning of this one?
Right.
And this is this is the main subject of this Hartle, Marx, and Witten, and they try to explain this one by using 100-page
but
paper.
This
so
shifting
this
doesn't change. I mean, the Liouville coupling, right? Because Liouville coupling is e to the phi c. I mean, the coefficient. What is coefficient? Please show me the action.
Now we should just shift to something like this.
So
that's why so Liouville interaction this term gives this one. So therefore, if we shift to something like this, then this just gives 1. So that's why this shift is allowed. Allowed is not so correct word, because if in the usual Liouville theory, phi is restricted to real value, then this is a complex solution. So this is not allowed. But now we are considering some kind of extended Liouville theory, where this phi takes complex value. B takes complex, and phi also take complex. So we are considering extended theory. That's why this kind of shift is allowed. And And yeah, this the aim of this paper is to explain this end. And it took 100 pages. But yeah, this is the subject I want to talk about from now. Yeah, this so once we have some solution, then we have another solution by shifting by this way. This can be seen from this one, and this is something we want to understand why this is allowed. Yeah. So yeah, but I'll talk about this one later in more detail. But anyway, once we have this kind of solution, then we can compute action. And as a classical one, then 2-point function should be sum over this one with all saddle. And one good thing here is that we know exact answer. So exact answer here. So what we have to do is just take a b to 0 limit of this expression. And this can be done, and we have this expression. And as I said, we can read off the parameter n from this expression. So because n appearing here, so from this one we can read off n. N is actually -1 at 0, and this value is actually half of if the wave function wave function square is related to Gibbon's Hawking entropy. So wave function itself is half of Gibbon's Hawking entropy plus some imaginary part. And so from this one, from this expression, we can read off Gibbon's Hawking entropy for correspond, and we can read off which geometry allowed in the Chern-Simons side. And this result exactly reproduces results by Witten by using conjugate CKS. This is our main result. And now we use, so in this specific example, we know exact answer. So we just need to take a semi-cluster limit, but this is not always the case. So not exact answer is not always available. So we want to have a more generic method. And this is what I want to say here.
Question?
Yes.
Yeah, so regarding this n equal -1, doesn't it mean that the negative Hawking entropy?
So this means,
Yeah.
so n equals 0 is a leading term.
Yeah.
And n equal if you take n equal -1, then this becomes negative.
Mm.
So I think this is just some correction for the Gibbon's Hawking entropy. Non-perturbative correction to this Gibbon's Hawking entropy. So leading one is positive.
Mm.
So there's negative. There's other contribution.
Mm.
This is the exponential. Yes.
I'm sorry, I have a very simple question.
Yes.
Is Liouville field is on the boundary or bulk?
A boundary.
And the dS, Euclidean dS does not have the boundary. So
We put some boundary at the future infinity.
in the
So we introduce some
Uh,
cutoff at
it's,
some finite time.
I mean, they, yeah,
CFT is living at some.
then does not relate you to Euclidean DS. Euclidean DS does not have the boundary. So in
Yeah, Euclidean DS just no
does not have
boundary.
boundary. So
And
it's T
yeah,
equals 0 case, T at T equals 0, viewable field is suddenly appeared.
yeah, this is somehow
Mhm.
yeah different from ADS CFT correspondence. So
Mm.
so in the so that's one reason why we are interested in DSCFT correspondence. In the DSCFT correspondence, if we consider Euclidean DS, then just no boundary. So where's the boundary? And the boundary is should be located in the Lorentzian case. There's boundary. So here. So question is what is relation between them? And yeah, this is something yeah we are studying here. So this there's some theory here, but we are somehow considering some complexified version of it. So there's some real part and the imaginary part, and the dual bulk theory also has a real part and imaginary part, and only imaginary part survives after taking square root of it. So from this one we have so from CFT we have real part and imaginary part, and the bulk side we have also real part of and imaginary part, and the only imaginary part can be seen from this one. So this one we also take some square root of it, so we can only real information survives. So this is something happening here.
By analytic continuation. I mean that to satisfy analytic continuation from the Euclidean to Lorentzian, you caught.
No, I mean we are.
It just does not relate to analytic continuation.
Yeah, we are
Okay.
considering complex theory and considering some slice of it, strange slice of it, and there's a real part and the imaginary part. We can read off only real part. Imaginary part, no, only imaginary part. Yeah, real part disappears by taking square root of it. So yeah, this is what is happening here. So, but yeah, honestly, I do not understand much about it. So what happening then this real part. So there's a lot of question about it. Yeah, but yeah, right now I can say only about the real part. And yeah.
Thank you for your kind explanation. Thank you.
Yeah.
Yeah, so okay.
Yes.
You mentioned for the entropy, n equal 0 is the leading term,
right?
And n equal -1 correspond to the non-perturbative correction. But if we add this leading term and non-perturbative correction, then entropy becomes 0. So is it possible to have 0 entropy?
No. We have a wave function, and the entropy appearing actually in the power of exponential. So we have this process.
I mean, I'm just considering this Gibbons-Hawking entropy. I mean, this expression.
Yeah, right. So yeah, Gibbons-Hawking entropy.
Of course, if we consider wave function, then maybe we may have different result. But if we just only consider Gibbons-Hawking entropy for the leading term and non-perturbative correction, then it seems to be vanishing.
No, this is definition of actually correction of Gibbons-Hawking terms. So if we take a square of this, then this becomes what?
So this only a wave function is meaningful.
What is it?
I mean
meaningful?
I mean this Gibbons-Hawking entropy for the integer n only appears in the wave function in this way.
No, so
But-
if we take square root of it, then we have subring tab appearing.
So we should lead up the corresponding entropy from the wave function. I mean the square of wave function. Is it true?
Yeah. Right.
Ah, I see.
No.
Okay.
Yeah.
Okay.
Right.
Okay. Then yeah, no problem, baby.
So this is something we have puzzles about it actually. So yeah. So we are. Yeah. This is something. Yeah. It takes actually many time to arrive this conclusion. So we are fixing some boundary field, and we are there's several saddle point in the geometry, and we have to sum over. So this path maybe I should. So this path integral. This path integral is defined by fixing some boundary value, but after fixing some value, we have several saddle points, and this path integral means we sum over all saddles. So this can be written as a sum over exponential of some saddles labeled by a. Yeah, and the wave function is basically so square of wave function is this one. This is basically definition of Gibbons-Hawking entropy. So that means wave function must be written in this form.
Okay, now I understand.
SGS. So if we compare this expression and this expression, then so only conclusion is that this part can be regarded as a sum of collections, not this one. So, yeah, actually this it took a lot of time to arrive this conclusion.
I see.
Yeah. And where am I? Now it's almost time is over. So how much I can use? Okay, maybe let me quickly. So this part is somehow ongoing work. So actually, there's nothing new, but I think this is somehow interesting. So I just briefly comment on it and conclude this. So this is somehow related to resurgence. Resurgence means resurgence connects a non-perturbative part and the perturbative part, or instanton sector and perturbative sector. And so let us ask. So usually, if we compute some say partition function by using Feynman diagram perturbatively, then we have this kind of asymptotic series. So partition function can be expanded by a coupling constant, but coefficient diverge. Coefficient is factorial, takes factorial 4 because the number of Feynman diagram increases if we go to a higher order of perturbative parameter. And one way to deal with this asymptotic expansion is Borel summation. So let us define this quantity divided by this factorial. Then this is a convergence quantity. And if we do Laplace transform of this, then we can go back to this one. So this Borel summation gives integral form of this asymptotic expansion. And if we assume this kind of form for large Q, then this sum becomes something like this, and this can be written by this. And if we plug this into here, then we can pick up some pole, and this term becomes something like this. So in this way, asymptotic series is related to instanton collection. So in this way, we can relate perturbative expansion and non-perturbative effect. And let me say more concrete in our example. Now we are considering two-point function dB theory, and but actually essential part comes from 1 over gamma. So let us consider 1 over gamma, the example. So we expand this one by instanton sector. So each instanton sector has this kind of factor. And let us assume that we do not know the coefficient, but let us assume this can be written in terms of sum over instanton sector labeled by some integer. The other part is we assume that other part is known. This is just a Stirling formula, and this is some perturbative part, but this is actually known. So for example, let us for simplicity, let us take a log of this one. Then this can become this one, and this part become this one. This is just Stirling formula, and this part is actually known to be given by this simple form. This becomes perturbative part, and this part is unknown, and we want to determine this one from the information of this one in the following way. So now we want to perform Borel dimension of this perturbative part. Then we have this expression. So here we have some pole here. So pole located here, and the contour is contour depend on argument of this parameter, and so depending on the argument, we have this contour on this contour, and if we change contour this and this, then we pick up poles, and so there's some value here. So we so there's difference between if we there's some ambiguity of this integral. So we can choose any contour, but if we contour change this to this, then we have this value. So there's some ambiguity of this amount for this integral. And in order to have a well-defined quantity, then this ambiguity has to be cancelled. And the philosophy of resurgence is to cancel this ambiguity from non-perturbative part. And now we have this one. So we have to choose a question such that if we cross the this argument is this one. This then we the G should be changed, and this is known as Stokes phenomenon. So we assume we require Stokes phenomenon happen when this value argument of this one crosses imaginary axis. So if real of this one is positive, then there's no non-perturbative effect. But if we cross imaginary part, then there should be some instanton sector, and this value is chosen such that ambiguity coming from this one is cancelled from this one. So in this way, we can determine non-perturbative part from perturbative information, and same kind of arguments can be done for 3-point function as well. But now we know actually exact form for 2-point function, 3-point function. So actually here I didn't have anything new about this analysis. I just rewrite known result in a different way. So now we are going to get some new result by applying this kind of procedure. So this is what we are doing right now. So this is the end of the talk. So let me conclude the talk. So complexifying geometry is useful, sometimes useful when we consider quantizing gravity. And today I study 3D Chern-Simons gravity from 2D Lie theory by using dS3 correspondence we have proposed recently. And we determine allowable saddle of 3D Chern-Simons gravity from semi-classical expression of two-point function of 2D Lie theory. And I propose another way to determine non-perturbative saddles by applying research. And this is currently I'm working on. And of course, today I talk about 3D Chern-Simons gravity, but it is welcome to apply generalize this analysis to other gravity theory like JT gravity on Tochita or Vasil theory on dS4 and so. Yeah, this is all I wanted to say. Thank you very much. Sorry for.
Thank you so much, Professor Yasuaki Ikeda.
Yeah, thank you very much.
Yeah, let's ask some questions. Really, any questions?
So regarding to Stokes phenomena,
Mhm.
that calculation is done in 2D Liouville theory, and
Right.
and then this n, I mean integer n is related to some instanton
Right.
configuration,
Right.
and so if we just regard this
this
Liouville,
This n is semi-n appearing
right.
actually.
But if
Yeah,
we regard this Liouville theory as a
Mhm.
two-dimensional theory,
Mhm.
and this Liouville theory is somehow correspond to the two-dimensional worldsheet string theory, then this this instanton is related to some worldsheet instanton, or it can be realized as some D-brane state in two-dimensional string theory.
I don't think so. I don't. So in I don't. So
Then how do you
so
understand
the
this?
main claim of this Hartle Witten is this one. This one is very difficult to understand in terms of Liouville theory. But the Liouville theory has a gravity theory, not gravity theory, but a Chern-Simons description. But in a Chern-Simons theory, as we so it is just a polynomial or conical deficit. So and this can be regarded as a like Yang-Mills instanton in this instance. So in the dual this Chern-Simons description, this n can be regarded as a really instanton number. But in the
which kind of instanton? Yang-Mills instanton?
Yang-Mills instanton. Yeah,
I
Yang-Mills
see.
instanton. Just gauge field, and the gauge field wraps many times. So this is nothing but Yang-Mills. So I mean Chern-Simons action takes some integer value. So,
right.
Yeah, this is really instant. But in the Liouville theory side, it's very difficult to understand what this n means. Yeah, this is just appearing.
But this n is related to the Stokes phenomena in the Liouville theory sense, right?
Yeah, that's right. That's right. So if we compute perturbative part, then we have this kind of ambiguity. And in order to remove ambiguity, then we should have some term which cancel this one. This is one way to explain.
Mm.
But the Liouville theory, it's not instant. It's
Not
some
instant.
from
Mm.
it's some parameter.
Further questions?
Yeah.
Yes.
Edwin?
Actually, I have
please.
two questions. So one is about AS3. So whether non-integer value of k is well defined, and second is about the zeta case. So in the zeta case, your Liouville theory has a complex or imaginary central charge, right?
Right.
So then I don't know what do you mean by the complex setters, but in that case, if you consider boundary CFT, can you consider some saddle point, saddle approximation by distant method for complex or imaginary central charge? Something similar to the Cardi formula for real central charge.
Yeah, actually, I started to this subject is actually understand your work about Cardi formula. So, but I cannot solve that problem. So that's why I changed subject to this way. So I wanted to derive a Cardi formula in this case, but actually I failed. I did not.
But I think according to your result, so in a different way you obtain two, saddle thing. So maybe if you try to back thing, you should find agreement in the partition function like that.
We can compute the partition function in the gravity side and the CFT side. We find agreement, but what you did is you can use a Cardi formula.
Right.
But Cardi formula is of course obtained for unitary CFT, and this cannot directly apply to this case. And I don't understand why Cardi formula works in this case. I started to understand that problem at the beginning, but I gave up that one. But basically what we do here is to understand what does it mean about this non-integer. So first of all, if we take negative k, then this means that just our theory is non-unitary. So much like the case of Dojita case. So that means in the gravity side we have actually conical excess conical geometry, but conical deficit is 2 pi n, so it's non-physical geometry. So in this way, gravity side is non-unitary and CFT is non-unitary. And so question is so whether non-unitary CFT is well defined or not. But what I can say is that so we have some symmetry of this theory. This is called W infinity lambda, and we can do some representation theory. So in that sense, we can study things by using the symmetry only. So we do not rely on we do not need to rely on unitarity. Just assuming symmetry and assign some consistency like associativity of observer or something, then we can get a lot of information about it. So this is something we have used. So if things rely on unitarity, then we cannot use in this context. So we have to use something. Do not use unitarity. And in this case, there's strong constraint coming from algebra, so we can do a lot of things. And one more thing I want to say is now we are working on a version of dS3 correspondence, but actually we can start from usual Gabadel-Gopakma proposal. In that case, we have a duality between Bashir theory on digital space and 2D coset theory at some truth limit, but with imaginary central charge. In this case, gravity theory is unitary theory, but CFT is non-unitary because of imaginary central charge. But this is okay because in the ADS CFT correspondence, ADS gravity of ADS and CFT at the boundary is really the same, equivalent theory. But the DF-CFT correspondence is something a little bit different. So as I said in this slide, so in the bulk side, we have to take some. So wave function is related to correlation function of dual CFT, and the physical quantity in the bulk is square root of it. So in some sense, CFT times complex conjugate CFT should be real to bulk gravity. So even one CFT has imaginary central charge, if we couple to some CFT with complex conjugate central charge, then maybe that theory gives some unitary theory. This is a kind of idea. So, yeah, but we do not know how to how to see the unitarity from this combined theory. So that's why we have a lot of questions. We do not know much about the CFT correspondence. So this is, I think, one of important issue or central issue. People working on the CFT correspondence, how to see the unitarity of gravity side from dual CFT. Dual CFT itself is apparently non-unitary, but in some way we should see unitarity of bulk theory, but no one knows how to see the unitarity from dual CFT. This is one very important question.
Okay, thank you very much.
Is there a Lorentzian interpretation of complex shadows?
Yeah, so now we are considering partition function, and if we take square roots, then Lorentzian part do not contribute. So, so yeah, wave function itself has Lorentzian parts. So maybe there's a way to see it, but currently I don't know. I have no idea how to see Lorentzian part. If we compute a partial function, it just disappears. We can see only Euclidean part. That's one, drawback of the current analysis. Yeah, this is also important.
So integer n can have two numbers, 0 and -1. And this number is related to some instanton number. Then n equals 0 is also a non-trivial instanton or a trivial case?
Actually, in this case, this can be actually easily understood. Just change the sign of Euclidean time. So we wrap this way or opposite way. That's all.
So n equals 0 is also a non-trivial instanton.
N equals 0 is usual geometry, and n equals -1 is just wrapping opposite way. So just a parity.
So the
so
somehow
no,
the orientation reverse.
yeah, right,
I
right.
see.
And
So
if we work
somehow
on
that corresponds instanton and anti-instanton, maybe. Am I true?
I don't know. So yeah, this is I think important question also because if we work on Chern-Simons theory, then usual Chern-Simons theory which consider some perturbation around trivial background A equals 0. But if we want to apply Chern-Simons theory to gravity theory, then A equals 0 is not A equals 0 cannot give non-trivial geometry. This is just degenerate geometry. So we have to think of we have to start from some non-trivial geometry from the starting point. So maybe we can call it as a instant, but this is just a usual geometry in a if we treat a Chern-Simons theory as a gravity theory.
Okay,
Yeah.
I understand.
Okay, so if there is no question, then let's thank again speaker Professor Yasuaki Ikeda.
Yes, thank you very much for
interesting
discussion. Yeah.
And yeah. So
Thank-
교수님 더 질문을
Yeah, I mean, Hikida-san, if your time is available, then I wanted to ask some more questions.
Yeah.
Actually, I'm going to this direction. Actually, Chern-Simons gravity is consists of two Chern-Simons terms, right? A and A bar.
Right.
And as you know, this Chern-Simons term coming from the boundary of instanton action, because instanton action is just total derivative. So it can be written as a boundary term. So if we consider four-dimensional,
what do you mean by instant action?
FHF. FHF can be written as D of something. This something is precisely Chern-Simons action, right?
You mean four-dimensional case?
Yeah, I am considering four-dimensional.
Yeah,
So
right.
if we have four-dimensional instanton action, but this instanton action can be written as D of something. The something is precisely Chern-Simons term. So if we have some four-dimensional manifold whose boundary is, I mean, the disconnected union of, for example, if we consider digit 4, and then digit 4 has two boundary at past infinity and the future infinity. So if we consider four-dimensional instanton action on digit space, four-dimensional digit space, then we have two kinds of Chern-Simons term. One is the defined on past infinity, and the other one is the defined in the future infinity with minus sign. So this is formally exactly the same as the Chern-Simons gravity in 3 dimensions. Of course, the detailed map is a little bit different. But if we just uplift this Chern-Simons gravity to 4-dimensional case, I mean the topological Yang-Mills theory, and then we have instanton action. So I want to understand your N in terms of instanton configuration in 4-dimensional sense. So I think so four-dimensional sense, I mean, the equation of motion of Chern-Simons theory is just the flat connection. So somehow we are considering transition amplitude or some scattering states defined on past infinity. Of course, in that case, SU2 connection must be flat connection. And then we have another Chern-Simons theory defined on the future infinity. But this SU2 connection must be a flat connection because this is just the Chern-Simons. And so I think that somehow this transition matrix or transition amplitude or scattering state is somehow interpolation from past infinity to future infinity by some instanton configuration. So
I think this number is somehow related to so we can introduce some conical deficit or Wilson line in the 3D Chern-Simons theory. And
I understand that situation, but I want to understand that number n in terms of four-dimensional instanton action, because this is just the mathematical identity. So three-dimensional Chern-Simons gravity can be written as the instanton action on some four manifold. This four manifold has boundary, two boundary.
I mean, in the boundary we can construct some configuration with deficit angle, and if we connect, if we introduce one other direction, then we can construct such kind of configuration. So maybe, we have some Wilson line in the
right.
And
actually, the local proof, only local proof for this topological theory is Wilson line.
Right.
Yeah. But this Wilson line can be also calculated in the four-dimensional setup.
Right.
And then the question is how to interpret this Wilson line observables.
But even the Yamir theory, we can construct some defect or Wilson line. So it's one-dimensional object. So I think it's
so one-dimensional, right? Some string propagation.
Propagation. Right. Maybe two dimension, right?
Right. Yeah.
Codimension one.
Yeah. But it is a little bit mysterious why only two values of n is allowed. And it's not clear what is the meaning of 0 and -1.
So in our context, I think we are so basically only the geometry we constructed at the beginning is allowed. So another one is just time reflection obtained by time reversal. So
time reversal.
Essentially there's only one geometry, but in the Chern-Simons description there's some duplication. And if we consider a higher spin gravity, we can do the same thing. And we have several saddles, allowed saddle, but they are related by a wide group of SUN. So maybe there's only one geometry, but in a Chern-Simons description, there's a lot, but in the sense of geometry, maybe they are equivalent. In the Chern-Simons description, there's
another small question. Another question is, for example, in ADS3 case, the boundary theory is because ADS3 has SO2,2 isometry. So somehow boundary theory is related to SL2,R times SL2,R conformal field theory. So, but we know the unitary representation of SL2,R has two cases. One is the discrete representation, and the other one is continuous representation. But in your case, you are considering Liouville theory, but this Liouville theory also has two representations, discrete and continuous.
Yeah. So if B is real, then we can construct some theory with central charges more than 25. Then we can construct a unitary theory. And for unitary theory, unitary representation is just continuously. But now we forget about the condition that B is real. So then theory is non-unitary. And there's so we can construct any operator, maybe written in this slide. So exponential to be alpha, and alpha can be arbitrarily a complex value.
Arbitrary complex value.
Yeah, and there's a degenerate state. Degenerate state. Yeah, degenerate state correspond to basically finite dimensional representation of SU to Lie algebra and what is it?